imagine this. You step into an electric car, and when you brake, it doesn't just get a tiny bit of charge back. It like massively recaptures energy, almost instantly.
Or, you pull out your smartphone, plug it in, and maybe 60 seconds later, bam, it's fully charged.
Yeah, exactly. That stuff.
Yeah.
It doesn't really feel like science fiction anymore, does it?
Not at all. It's right on the edge of what's possible in energy storage. And it's forcing us to rethink these old rules, these trade-offs between batteries and capacitors.
Right, the whole power versus energy thing. For the longest time, it felt like this fundamental limit in tech, this gap.
That's it, the Ragone gap. You either got high power or high energy, but getting both in one device, that was the challenge.
So our mission today is to really dive into that gap, see if it's actually closing. We've looked at a bunch of research comparing, standard lithium-ion batteries.
Yep, the workhorses.
Conventional supercapacitors, and also what's coming up with solid-state tech. But there's this one specific breakthrough that caught our eye.
The M-rGO. Multi-scale reduced graphene oxide.
That's the one. So the core conflict, just to set the stage, is really basic, isn't it? Batteries use chemistry, slow reactions, but they pack in a lot of energy, high energy density.
Right. Think long distances, long storage times. But supercapacitors, or SCs, they skip the chemistry. They store charge physically, electrostatically, on a material surface.
Which means they're incredibly fast. Charge, discharge, boom. Insane power density.
Intense power density, yeah. But historically, that speed came at a huge cost.
You got the speed, but you lost all the endurance. Like you got the sprinter.
Who runs out of breath after 50 meters. And it's
Exactly.
not the marathon runner.
So we're here to dig into the actual numbers, the metrics, that show how maybe, just maybe, that trade-off isn't so absolute anymore. Let's start with the established players.
Okay, well, when you talk energy storage today, lithium-ion, LIBs, they're still king of the hill for energy capacity. They're built for endurance.
And their big strength is obvious.
Yeah.
Energy density. You see numbers like what? 200 to 300 watt-hours per kilogram?
Yeah, in that range typically. And volumetrically, maybe up to 700 watt-hours per liter for some really high-end cells.
And that's what gets you that, 600-kilometer range in an EV or lets utilities store grid power for hours. It's all about packing in the watt-hours.
But that chemical storage, that's also where the weaknesses creep in. The power density. It's okay, maybe around 3,000 watts per kilogram, but not amazing.
And the big one, the lifetime. The cycle life.
That's the real killer, often. You're typically looking at under 3,000 full charge-discharge cycles before performance really drops off, which sounds like a lot, but for heavy use.
It adds up fast. And then there's the other stuff, right? Manufacturing emissions, relying on lithium, cobalt, nickel.
Big supply chain and geopolitical concerns there, absolutely. Plus the safety aspect, that liquid electrolyte inside, it's flammable.
Yeah, the whole thermal runaway risk, not ideal.
Definitely not. So, okay, now contrast that with the conventional supercapacitor, totally different beast. The champion of power and longevity.
Pure physics, right?
Yeah.
Electrostatic storage, no chemistry wearing out.
Exactly. It's just charges moving onto and off a surface, so the power density numbers are just wild. Up to 10,000 watts per kilogram sometimes.
No.
Huge bursts of power.
And the cycle life, it's almost unbelievable.
It really is. Often over 1 million cycles, maybe more. That's like hundreds of times longer than a typical Li-ion battery. It basically lasts forever in many applications.
Okay, so that speed, that lifespan, perfect for certain jobs, like quick bursts.
Yeah, think grid stabilization, smoothing out power fluctuations, or capturing that massive surge of energy when a train brakes regeneratively, stuff that happens in seconds.
But here's the but, the classic problem. That low energy density.
That's the historical Achilles heel. Conventional ACs were stuck down around maybe 10 watt-hours per kilogram, sometimes less.
10, okay. So compared to the 200 to 300 HKEO for Li-ion, yeah, that's a massive difference. You need way more material, way more volume to store the same energy.
20, 30 times more. Yeah, they were sprinters, definitely. But they couldn't hold much energy. And another issue, they tend to leak charge over time, self-discharge.
Oh, right. They lose charge just sitting there.
Yeah, quite a bit sometimes. Maybe up to 50% in a month for some types. Compare that to Li-ion, which might lose only 5% or so.
So, okay, endurance versus speed and durability. That was the absolute trade-off for decades. You picked one.
Pretty much, until materials science started throwing curveballs.
Which brings us to graphene. Researchers have looked at graphene for ages, right? Because theoretically it has this enormous surface area.
Huge. And more surface area means more places to store that electrostatic charge. It seemed like the perfect material for supercapacitor.
But there was a snag, a really big physical snag.
A very sticky snag. Graphene sheets, especially when you try to process them, they have this really strong tendency to, well, restack, to clump together.
Like wet plastic wrap.
That's a great analogy. It's called agglomeration. And when those sheets stack up flat against each other, driven by these intermolecular forces, poof, most of that beautiful surface area is gone, sealed off.
Defeating the whole purpose.
Yes.
And keeping that energy density disappointingly low.
Exactly. Which leads us to the breakthrough from Monash University. This multiscale reduced graphene oxide, M-rGO, and critically, how they make it.
They start with natural graphite, which is like everywhere.
Right.
Abundant.
Very abundant. Good for scalability and avoiding resource bottlenecks. But the clever part is this rapid thermal annealing process they developed. It's a specific way of heating it.
Now, hang on. You said rapid thermal annealing, which sounds like just heating it fast. How does simply heating it differently solve such a fundamental problem like sheets sticking together?
It sounds simple, but it's about controlling the structure that forms during that rapid heating. It's almost like intentional chaos. The quick, intense heat doesn't give the graphene layers time to settle into those neat, flat stacks. Instead, it forces them into this unique, highly curved, tangled structure. There are ordered bits interwoven with disordered bits. Think less like a neat stack of paper and more like a loosely crumpled ball of paper, or maybe a sponge.
So the structure itself physically stops the sheets from lying flat and sticking.
Precisely. It props them open. And here's the really cool scientific bit. This specific tangled structure allows the electrolyte ions, the charge carriers, to actually force their way between the layers when you apply a voltage.
They wedge them open?
Kind of. The researchers call it operando electrochemical interlayer expansion, or EIE for short. Basically, charging the device helps to push the layers apart slightly, opening up even more internal surface area that was previously inaccessible.
Wow. Okay. So by creating this sort of controlled messiness in the architecture, they're fundamentally changing how charge gets stored and just unlocking way more usable surface area.
You got it. And that leads to some pretty dramatic performance improvements.
So what are the numbers? What did this M-rGO actually achieve?
Okay, the big headline figure, especially thinking about practical applications like in devices or vehicles where space is tight, is the volumetric energy density. At the stack level, using ionic liquid electrolytes, they hit up to 99.5 watt-hours per liter.
99.5 WHL. Okay, wait, that's still way less than the, say, 700 WHL for top-tier Leon. So why is that number? Almost 100 WHL, such a big deal.
Because it completely changes the conversation compared to other established technologies. That 99.5 WHL puts these M-rGO supercapacitors squarely in the same league as, or even better than, traditional lead-acid batteries.
The old car battery tech, the ones in forklifts, backup power.
Exactly. Those typically only manage maybe 20 to 50 watt-hours per liter. So M-rGO offers better energy density than lead-acid, while still giving you that incredible supercapacitor power density and that million-cycle lifespan.
Okay, that's the commercial aha moment. You're not trying to beat Lion on pure energy density yet. You're offering a direct, superior replacement for a huge existing market lead-acid with none of the environmental baggage of lead.
Precisely. It's a zero-compromise replacement for a massive multi-billion-dollar legacy technology. And like you said, ditching lead is a huge environmental win.
Plus, the sources emphasize the scalability, right?
Right.
Because it's just a modified heat treatment on abundant natural graphite.
Correct. It avoids those difficult supply chains for lithium, cobalt, nickel that plague LIBs, so potentially much more sustainable and geopolitically stable.
And it still keeps the power.
Oh, yeah. The power density remains extremely high, over 69.2 kilowatts per liter. And the capacitance itself, just the raw charge storage ability per gram, jumps significantly too. Around 140 farads per gram for M-rGO, compared to maybe 35 FJ for typical activated carbon used in older SCs.
Okay, so M-rGO is a huge step. It makes supercapacitors genuinely competitive for replacing older tech and maybe playing a new role. But let's look at the other challenger coming for Lion, solid-state batteries, SSBs.
Right. If M-rGO is boosting the supercapacitor's energy, SSBs are coming at Lion's weaknesses from the other side, aiming for even higher energy density and critically better safety.
The safety angle is huge. They get rid of that flammable liquid electrolyte.
That's the core innovation. Replace the liquid with a non-flammable solid electrolyte. That immediately tackles the thermal runaway risk, which is a major concern, especially for EVs and large grid storage.
And using a solid allows for different chemistry.
Exactly. That stable solid structure makes it feasible to use lithium metal anodes instead of the graphite used in most current LIBs. Lithium metal can theoretically store much more energy.
So the goal is even more range.
A lot more. The target is aggressive. SSBs are aiming for potentially 70% higher energy density per unit volume compared to today's Li-ion. That's the kind of leap that could really transform EV adoption.
Okay, sounds amazing. But the challenges, they seem really tough, making ions move through solid efficiently.
It's incredibly difficult. That's a good way to put it. Like forcing water through concrete. They face really three major hurdles right now.
Okay.
First, just keeping good, stable physical contact between all those solid layers as the battery charges and discharges. Solids don't flow like liquids to fill gaps.
Right, if a gap opens up, the ions stop flowing.
Exactly. Second, managing the volume changes. That lithium metal anode, when it plates and strips lithium during cycling, it physically expands and contracts quite a bit, maybe 15 to 30%.
Whoa, so the anode itself swells and shrinks that much inside a rigid solid structure.
Yeah. And that physical stress can cause cracking, loss of contact, all sorts of problems that kill the battery's lifespan. It's like inflating and deflating a stiff balloon inside a glass box over and over. Eventually, something breaks.
Ouch.
Okay.
So contact and physical stress, what's the third?
The third is what you mentioned, ionic conductivity. Just getting those lithium ions to move quickly and easily through the solid electrolyte material, especially at normal operating temperatures, like room temperature, it's fundamentally harder than moving through a liquid.
So lots of hurdles still.
Sure.
What's the timeline look like for SSBs?
It's still ways out for widespread commercial use. Projections are often pointing towards 2027, maybe later, before we see them making a significant impact in the market. There's still a lot of fundamental material science and engineering to solve.
Okay, so we've got Li-ion, the reigning energy champ with its issues. We've got M-rGO supercapacitors, the speed and cycle life champ that just got a serious energy boost, enough to challenge lead acid right now. And we've got SSBs, the future high-density, high-safety contender, but still under development. Let's talk cost and environment for a sec. How do the SECs stack up right now?
Well, upfront cost is definitely a challenge for graphene SCs currently. The materials, the more complex manufacturing for something like M-rGO, it accounts for a big chunk of the cost, maybe 70%. And they just haven't hit the massive production scales that Li-ion has, which is what really drove lag prices down over the last decade or so.
But the environmental angle, especially with that insane cycle life.
Yeah.
That has to count for something, right?
Oh, absolutely. That's the long-term win for SCs. You're using abundant carbon, not problematic metals like cobalt. They're generally less toxic. And if a component lasts for 1 million cycles, maybe 50 years in some applications, you're just not replacing it nearly as often. That dramatically reduces waste.
Compared to Li-ion, where recycling is still kind of tricky.
Yeah, Li-ion recycling is improving, but the infrastructure isn't fully built out yet. And the processes themselves can be energy intensive and complex because you're trying to separate out all those different materials cleanly.
And we are seeing these high-power, long-life supercapacitors finding real jobs already, aren't we? Where those specific strengths are needed.
Definitely. We mentioned trains, right? Companies like CRRC are using graphene SCs specifically for regenerative braking, capturing huge amounts of energy in seconds, then delivering it back for acceleration. A battery just couldn't handle those power surges repeatedly without degrading super fast.
And data centers, too.
Yeah, think of our AI data centers. Huge power demands, absolutely critical reliability. Companies like Skeleton Technologies have these graphene battery backup units. The SCs provide that instant high-power backup and handle frequency regulation tasks, again, that need immediate response and tons of cycles.
Okay, so if you step back, Li-ion for long energy storage, M-rGO supercapacitors for power, speed, incredible lifespan, and now decent energy density.
Yeah.
It really feels like the answer isn't one winner, is it?
No, I think that's exactly right. The future almost certainly is complementary. It's about building hybrid systems. That's how you effectively bridge that Ragone gap in the real-world application.
Combining the strengths.
Precisely. You design a system where the supercapacitor component, maybe using M-rGO to make it more energy dense and viable, handles all the really stressful stuff. The quick bursts of power for acceleration, soaking up regenerative braking energy instantly, smoothing out grid demand peaks.
Taking the hits, basically.
Taking the hits, yeah. And by doing that, it shields the Li-ion battery component from that damaging high-rate cycling it doesn't like. The battery can then just focus on what it does best. providing the long-duration, steady energy storage.
And the result is you make the whole system better.
Much better. You dramatically extend the operational life of the expensive Li-ion part because it's not being stressed as hard. That lowers maintenance, lowers replacement costs, reduces overall waste. It's a win across the board. For something like a smart grid, you get the best of both worlds: the long-term storage from the battery and the rapid response from the SEC.
So the big takeaway here seems clear. This M-rGO development is genuinely significant. It makes supercapacitors a practical, commercial reality for replacing old tech like lead acid right now, and it makes them a much more powerful partner in hybrid systems with Li-ion.
Absolutely. Li-ion is still the king for pure long-duration energy density for now. Solid-state batteries are the ones aiming to take that crown eventually, focusing on even higher density and safety. But M-rGO is changing the game today by dramatically boosting the capacitor side of the equation.
Which leaves us with a final thought for you, the listener, to chew on.
Yeah, think about this. If these sophisticated hybrid systems, using tech like M-rGO SCs alongside batteries, can massively increase the lifespan of the whole system and significantly cut the environmental impact, does the focus maybe need to shift?
Shift from what?
From this relentless quest for one single perfect battery chemistry that does everything, towards optimizing the entire system architecture. Maybe the future isn't about finding one magic material, but about cleverly engineering systems using the best features of different components we already have or are developing right now. It becomes less about pure chemistry discovery and more about smart system design. What do you think?